Good morning, good afternoon, or good evening, students. Today we're going to talk about scientific notation and the metric system. You need to download and look at this PPT that I am talking about here, and you also need to download and look at the Word document that is also in this location. Okay, the metric system part one. Part one refers to the fact that this information is going to help you finish part one of the assignment that is on your Word document. The Word document is what you're actually going to be filling in and turning in. So, can anybody do this? This is not the metric system, so that means we have a frowny face. 3.7 gallons to teaspoons. Well, guess what? I cannot do that. I do not remember how many teaspoons there are in gallons, and even if I did, I don't think I could do the math in my head anyway. How about this one? Convert 3.7 liters to milliliters. A quick intro on how much is a liter. Well, 3.8 liters are in 1 gallon, so this is about 1 gallon actually. Milliliters, how big are those? Well, a shot of liquor is around 44 milliliters depending on the country, and I looked it up online. I didn't know, but it's something like that. You get a bunch of different results. If any of you are bartenders, feel free to correct me on the discussion board. I think I remember reading it's 30 milliliters sometimes, or 50 milliliters, or 1.5 ounces. But anyway, in a shot of liquor, something like this. That's about how much those are. This conversion, I can do it in my head easily because I can remember a few things. This root word, milli, means thousand, something like a thousand or thousandth, thousand. Let's do it that way, thousandth. So there are 1,000 milliliters in a liter. So to do this conversion, what we're going to do is just take 3.7 and multiply it by 1,000, and this is pretty easy math because it is in base 10. So 10, 100, 1,000, 10,000. This kind of math is pretty easy to do in your head, and some of you, I'm sure, have already done this. 3.7 times 1,000 means you're going to move this decimal place over 3 times. So 1, 2, 3, or 1, 2, 3, and then we'll fill in those zeros there. 0, 0, and we got our decimal point there. Oopsie. And then we'll have a comma. So to write that neatly equals 3,700. Move the decimal point over 3 places because there's 3 zeros there. All right, the metric system, again, here is not the metric system. 3.7 gallons to teaspoons. How do we do it? I'm going to go through this one really slowly for you. And this manner of doing conversions can and should be used to do conversions in the metric system. It's a way of guaranteeing that well, it's not a way of guaranteeing, but it's a way of checking that your answers are correct. So you're going to use the units. So include the units here when we do the math. 3.7 gallons. 3.7 gallons. First one is we're going to convert it to the next smallest thing. We're not going to go all the way to teaspoons simply because I want to illustrate my point of how difficult it is to move through our system. 3.7 gallons, first converting goes to quarts, so 1 gallon equals 4 quarts. How we would do that is like this, 3.7 gallons times 4 quarts. I'm not sure what the correct abbreviation is because I never use quarts because I only use the metric system in science, but 4 quarts in 1 gallon. Now, how algebra works is if the 3.7 gallons, this is going to be on the numerator. 3.7 times 4 quarts, that'll be on the numerator. So what happens here is gallons and gallons are going to cancel out, and then we're going to get whatever 3.7 is times 4 is going to give us some number. Okay, and then quarts is going to be the units remaining. So we've now converted 3.7 gallons to quarts because there's 4 quarts in 1 gallon. So 3.7 gallons times 4 quarts. And moving to the next one. So 1 quart equals 2 pints. So 2 pints, P for pints, I guess, divided by 1 quart. And again, the units cancel out. Quart and quart cancel out. That's how algebra works. And then we do the next one. Let's see. So 1 pint is 2 cups. So let's see. 2 cups per 1 pint. And then pints cancel out. And holy smokes. And then let's see, from cups, so 1 cup equals 16 tablespoons. 16 tablespoons. That's a very ugly 6. 16 tablespoons divided by 1 cup. So then the cups cancel out, and then 2 times 16, yeah, and then teaspoons. Lastly, we're almost done. 1 tablespoon times 3 equals 3 teaspoons. So there's going to be 3 teaspoons per 1 tablespoon, and that is going to equal something. I'm going to pause this right for real quick to do this math with a calculator because I can't do it in my head. 3.7 times 4 times 2 times 2 times 16 times 3 is going to equal something. The denominator here, 1 times 1 times 1 times 1, we can basically ignore it because that's how you multiply fractions. Okay, I just took some time off there. I did it on my cell phone calculator, and what I got was 3.7 gallons is 2,841.6 teaspoons. Holy smokes, did I do that right? I'm going to pause it again and do my math again because I'm so uncertain. That was just so much math, I could have made a mistake. Okay, and we're back. I just checked my math and I did do it correct. Huzzah! If I made a mistake in here, well, you can feel free to correct me, and you know, every now and then I embarrass myself like that. But point is, it's really tough to do conversions outside of the metric system. The metric system is much easier. So let's go back to this other problem. 3.7 liters to milliliters. 3.7, I managed to delete that question. 3.7 liters equals how many milliliters? Okay, so let's take a look at these root words over here. The standard unit is we're going to put it here, and I'm going to use just liters, for example. So if we have 1 liter, then there's all of these root words over here. Deci, centi, milli, micro, nano, and pico. So let's go through a few of them. Deci, that means essentially a tenth of a liter. So 1 deciliter is going to be 0.1 liters. 1 centiliter, 1 centiliter is going to be 0.01 liters. And a milliliter, that's the one I'm interested in right now, is going to be 1,000th of a liter. I'm going to keep going for a few more, and then micro, 1 microliter. That, now I'm going to start having trouble writing this all. That is going to be 1 millionth of a liter, 0.00001 or 10 to the negative 6 liters. Really small. Nano is a billionth of a liter, or a billionth of something. Pico is a trillionth of something. And then going in the opposite direction, deca, this is 10 of them. So that's, instead of 1/10, that's 10 liters. So a decaliter would be 10 liters. And remember, it's something like 4 liters equals a gallon. So if we had a decaliter, that'd be like about 2.5 gallons or something like that. Hecto, that is 100. I'm writing these over here because I like writing. It keeps my brain occupied, but you can see it's written here as well. 10 squared, or 100 liters. Kilo, that means 1,000, so 1,000 liters. So this would be really a lot of something. And then mega is a million, giga is a billion, tera is a trillion. And some of these you might be a little familiar with, like kilo is in a kilobyte. If we change the units here to computing terminology, a byte, a byte, then these we ignore in computer land. But a kilobyte is pretty small. It's 1,000 bytes. Then a megabyte, now you're starting to talk about maybe the size of something on a picture on your phone. A megabyte's a million bytes, a gigabyte is a billion bytes, a terabyte is a trillion bytes. So 3.7 liters time equals how many milliliters? Well, it's pretty easy. I know that there are 1,000. How should I explain this differently? A milliliter is a thousandth of a liter. So another way of saying that is that 1 liter equals 1,000 milliliters. So again, now that I have these root words memorized, milli, that means a thousandth. So 3.7 times 1,000 equals 3,700. Please do include your commas when you are writing for this assignment because that is how numbers are written correctly. Okay, I'm going to erase all of this math here. Hope you figured that out, but I guess you can kind of go back in time with this lecture and just read it again. Come on. Oh boy, there's a lot to erase, isn't it? Okay, that's good. All right. So some of these terms you absolutely are going to need to remember for science. Let's get those erased as well. For science and more importantly for you probably for this class. So which ones are they? So we're going to have some type of base here, and it's going to be 1. So it could be 1 liter, or 1 meter, or 1 gram, maybe. This is the base unit, or the standard unit, the SI unit, they're also called. You also need to memorize for this class, and I mean memorize. Like you've got to, commit it to memory completely. Somethings. This means a thousandth. You need to memorize. Micro, this means a millionth. These are really important in biology because micro, these units are what we use to measure the size of things like cells and even organelles. Bacteria is something like between 1 and 5 micrometers, micrometer, a millionth of a meter. And then also this one you need to memorize as well. A nano something or other. So like a nanometer, that'd be a billionth of a meter. A meter is approximately a yard. A billionth of a meter. Why do you need to memorize it? Because you need to be able to be literate when you are reading biology. Nano somethings, nanometers, those would be used to measure parts of cells, such as the cell membrane is something like 7 nanometers wide. Molecules are also measured in nanometers, and we'll come back to this later in this lab. Pico, that's a billion. I'm not asking you to memorize these things because I do realize that we live in the world of the internet and you can look these things up pretty easily. But these ones, milli, micro, nano, you're going to be reading them all the time. And if you're going into any science-related field, you have to know them. You cannot be looking these things up all the time. This is about being scientifically literate. A couple other ones. Kilo, you got to have that memorized. This one's going to come back to bite you in terms of kilograms. Kilograms are really common. Pretty much every country in the world uses kilograms to measure things like body weight. The only exception really being the UK and maybe some other Commonwealth countries where they are familiar with what a pound is, but they're sort of like, oh, really? Pounds? You're using pounds, huh? All right. Kilogram. So these that are highlighted, commit them to memory. You got to remember. Oh, except for pico whatever's. But these ones you've got to memorize them. Kilo, the base, milli, micro, nano, and the base that would just be M for meter, L for liter. Let's see what was with and for mass it could be gram. So these are the base right there. Okay, cool. The metric system, more of that. All right, why is this still here? Right, I already did that for you. I got a little ahead. Okay, so scientific notation and standard notation. So how would you say this number? The answer is I do not know. It's a really big number. Oops, I already said that. The answer is 1 quadrillion, and then of course we could just keep kind of going with this example, making it even more absurd. How would you say that number? I also don't know. How would you say that number? I also don't know. And this is why we have scientific notation. What this is standard notation. Standard notation just seems pretty standard. There's commas and it's a big number. Well, I'll get to what scientific notation is in a minute. This is a huge number, and this is, for example, synapses. Those are connections between neurons in a child's brain. There are 10 to the 15 synapses, or connections between neurons in a child's brain. So I can just say 10 to the 15, 10 to the 15, and that communicates a number that is insanely big. This 15 means that we're actually talking about a 1 followed by 15 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then we fill in the commas. 1, 2.5, 2, 3. Yeah, and I don't know how to say this number. It's a big one. Million, billion, trillion. Oh, that's again a quadrillion. What a coincidence. 10 quadrillion or 1 quadrillion synapses between a child's neurons in their brain. Pretty cool. Okay, so a little bit of background information on scientific notation. And we're going to start with what exponents are. So for example, 2 squared, what 2 raised to the second power, a couple terms, that's called an exponent, and you need to know that. The 2 here is an exponent, and so what that means is when you have 2, that means that you're going to take whatever the base is, this is the base, and you're going to multiply it by itself, basically 2 times, or sort of like 2 times 2, because there's a 2 there. So 2 times 2 is going to equal 4. Now, if you had something like 2 to the third power, then that means you're going to go 2 times 2 times 2. So 3 of them, 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. Same thing with 2 to the fourth power. Means there's going to be 4 of them getting multiplied. 1, 2 times 2 times 2 times 2. And that's going to equal, let's say 2 times 2 is 4, times 2 is 8, times 2 is 16. All right. Now, in scientific notation, this becomes a little easier because we're always going to be using 10 as the base, and then we're going to be adding exponents of some size. So it could be 2, in which case it's 10 times 10 equals 100, right? Or if it's 10 raised to the third, then it's going to be 10 times 10 times 10 equals 1,000. Include your comma. And you can probably guess that basically if you have a huge number, like say 10 to the 6th, then you don't need to write all this out. Whatever number is here, as long as we're working it with a base of 10, then if the exponent is 3, then there's going to be 3 zeros, right? So there's 1 0 there, 1 there, and 1 there. And all right, so 1, 2, 3, and 3 here, 3 there. So there's 3 zeros here. So if it's 10 to the 6th, we can simply say 1 and then 6 zeros. 1, 2, 3, 4, 5, 6. So the point being is that we can pretty quickly develop an intuitive knowledge of what a number like this means, and we can even calculate it out very precisely. So that's how exponents work. Now, exponents can also be negative. So if we had I'm going to start just using tens now because it's easier math, and that's what we use in scientific notation. If we had 10 to the negative 2, what that means is, well, you can't really do much with 10 to the negative 2 in terms of handwriting or writing it out. You can't go, it's not negative 10 times negative 10. That's not what it is. What we do is we would go negative 10 to the negative second power equals 1 divided by 10 times 10. Or I guess I kind of skipped a step. 1 divided by 10 squared. So 1 divided by 100, we probably know is 0.01. Yeah, 1 divided by 100. If I was going too fast for you, I don't think I was, but 1 divided by 10 squared is 1 divided by 100. And when you divide something by 100, it means you're going to take this decimal point right there and move it 2 spaces to the left. So how did we get this number here? Let me just go from here, 1 over 100. We're going to take the decimal point and we're going to move it to the left, 2 spaces. So this equals 0.01. Decimal point is there. There we go, 0.01. So point being, 10 to the negative 2 equals 0.01. How can we shortcut this? Well, when it's a negative 2, this is a little bit more confusing, but the decimal point is not obviously right here. The decimal point is actually right here. But simply because, you can look back here, what we do when the exponent is negative is we put 1 over this whole value. So 10 to the negative 2, we go 1 divided by 10 times 10, or 1 divided by 10 times 2. Let me give you another example. 10 to the negative third is going to equal, I'll do it the long way, 1 over 10 cubed, or 1 over 1,000. When you're dividing something by 1,000, it means you're going to take the decimal point and move it to the left 3 spaces. So 1. Here's our decimal point. We're going to move it 3 spaces to the left. 1, 2, 3. Oops. 0, 0, and there's our decimal point. And 0. So 0.001. And written more neatly, 0.001. Okay, so that is an introduction to exponents and what we do with exponents. So now let's take an example, or take a look at converting from standard notation to scientific notation, and this is also on part 1 of your assignment. So this is a really big number, and it's kind of annoying to say, 624 billion, and then if we had an even bigger number, like say we added 15 zeros, then we wouldn't even be able to say it. So how can we turn this into scientific notation? First rule is we take the first first number, placeholder there, it is 6. And then we're going to put a decimal point right after the first number. So 6 point something, 6.24. Now, instead of all these zeros, instead of writing those out, we're just going to write times 10. So 6.24 times 10, does that equal this number? No, not at all. 6.24 times 10 equals 62.4. So, excuse me, if we did this, calculated this, then it would equal 62.4. So this is not scientific notation for this number. What would be? So we need to get whatever number we're going to put here, 6.24 times 10 to the something. 10 to the something. So the decimal point is, we have moved, what we want to figure out here is what exponent do we need to put here to make this value equal this value. And it's pretty simple. We can just count out the number of spaces that we would need to move this decimal point that way to equal this number. So 6.24. Let's put 6.24. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So 6.24 times 10 to the 11th power equals this number. Did I do it right? Let's see. 6, 2, 4. And to do this math, I would take this decimal here and move it to the right 11 spaces. So from there, let's see, starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There it is. Now I'll fill in the zeros. 1, 2, 3, comma, 1, 2, 3, comma, 1, 2, 3, comma. Did I get it right? I did. 624 billion. 624 billion. Great. How about this one? We have a really small number. This is right here, standard notation, and we want to convert it to scientific notation. All right, let me just give myself some space here. Da, 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 da. Okay. By the way, sorry if I'm going a little slow, but it's kind of better to make sure that, in case some of you weren't too good at math in high school or whatever, that I want to give you some background here. So what do we do here? In this case, we are again going to look for a number that is not a 0, and we can put a decimal point right after it, and that is going to be 4.3. So we put the decimal point right there. And 4.3 does not equal this 0.00043. Obviously, these two values are not equivalent, so there's a problem here. We're going to have to add times 10 to the something. So 4.3 times 10 would be 43. So that's obviously not right. We are going to need to add an exponent, and the exponent is going to have to be negative because we want this decimal here to go to the left, so that it would be in the same place as it is on this side. So we count out decimal points here. If we want to move it, if it needs to go that way, that many spaces, however many, then let's count them out. 1, 2, 3, 4, 5, 6, 7. 7 spaces, so negative 7. 4.3 times 10 to the negative 7, and this is scientific notation. 4.3 times 10 to the negative 7. Now, things that students will do that are wrong. Remember, does your exponent need to be a negative or a positive value? If you are converting a small number, this is a small number, to scientific notation, then the exponent's got to be negative. And if you're converting a large number to scientific notation, then it's going to be positive. And you don't write a positive, you just write the number. So 4.3 times 10 to the negative 7th. And if we really wanted to test this out, why don't we? 4.3. Oh, whoops, no, I didn't do that right. That's because I'm going to be moving that decimal in the other direction. So let's give myself some space here. 4 point, right, and decimal is there, and I'm going to move it to the left 7 spaces. So from here, 1, 2, 3, 4, 5, 6, 7. There's my new decimal point, and now I add the zeros. 1, 2, 3, 4, 5, 6. So there's 6 zeros over here. Let's see, 1, 2, 3, 4, 5, 6. Okay, so I did it right. That is scientific notation. And that is how you go from standard to scientific notation. You're probably going to get a question like this on this week's lab quiz and the test at the end of a couple of weeks here. And how would we go from scientific notation to standard notation? Well, let's say we have a number such as 3.2 times 10 to the 8th. 8. That means we're going to take this decimal point and move it that way 8 spaces. So 3, 2. Here's my decimal point right here, right? And we're going to go 1, 2, 3, 4, 5, 6, 7, 8. There it is. And then we fill in the zeros. Okay, and then we add our commas. 1, 2, 3, and 1, 2, 3. 320 million. So that's 320 million. 320 million. That's a big number. you put in the commas, all right? That's how you write numbers. When you don't put those commas in, it is confusing to read it, and people often, it makes it more work for the reader to read. So if you don't add those commas, you'll lose points if this was a quiz or a test. Okay, let's give you another example, another real easy one. Let's say 9.648 times 10 to the third. Okay, so that's 1,000. 10 to the third is 1,000. And it means that we're going to take this decimal point and move it that way 3 spaces. Now, do you need to memorize, moving the decimal point to the right 3 spaces when it's 10 to the third? Well, yeah, you could look at it that way, but conceptually, think about it like this. 9.648, whatever, small number, 10 to the third. That's a big number. So what we should get is a bigger number. So 9.6 is going to grow. 9.648. 9.648, that's not even 10. And when you multiply it by 1,000, it's obviously going to get bigger. So we're going to take the decimal point that is there, and it's going to go 1, 2, 3. It's there. So now we actually have 9,648. Yay. Okay. And what about doing this in the opposite sort of direction? Opposite? No, it's not really an opposite. But what if we have a negative exponent? That's often the one that will confuse some students. Again, for those of you who this is kind of easy, sorry, but students need to know this, so we got to go a little slow in case some students don't. So let's go 4.17 times 10 to the negative, what's a good number? 7. I like that number, 7. To the negative 7. So negative 7, 10 to the negative 7, that is 1 over 10 times 10 times 10 times 10 times, how many? 1, 2, 3, 4, 5, 6, 7. Oh. So that's a lot of 10s underneath a 1. So this is basically, that's that, and it's a small, very small, with an exclamation point even. Let's even add 2 exclamation points. Ooh. Small, very small number. When you multiply anything by a very small number, then this number is going to get smaller. So if the exponent is negative 7, then we're going to take this decimal point and move it that way to the left 7 spaces. So here we go. I'm going to start over here. So 4.17 decimal point. It's going to go that way 7 spaces. 1, 2, 3, 4, 5, 6, 7. Fill in the zeros. 0, 0, 0, 0, 0, 0. So I'm going to got to put one there too. 0.000000417. That's gone now. All right, so this is standard notation, and this is scientific notation. A couple of things about that I've already said, but I feel compelled to say them again. Scientific notation, 3.88 times 10 to the 4th, we'll say. Couple of things. The decimal point is always here. So this is correct. And 38.8 times 10 to the third. Now these two numbers, 38.8 times 10 to the third, is the same value as 3.88 times 10 to the fourth. They're the same value, but this one correct, this one wrong, and simply because scientists have standardized the way that they write large numbers. You don't write 38, you write 3.88. So the decimal always goes after the first integer in scientific notation. So this is now part 2. So what I'm going to be talking about here is going to be in reference to part 2 of your assignment. The standard unit for length, maybe I'll use red here. The standard unit for length and distance is not a kilometer, not a centimeter, it's a meter. And so we would write out here, what I'm asking you to do in the assignment is fill in these blanks. The directions say that on the assignment. So you fill in the blank. So the M stands for meter. You absolutely have to have that memorized because it is standard everywhere across the world and in science. If you're from abroad, this is probably like super easy. This is like teaching you what an inch is. A meter is, oh dear, can I remember what it converts to in feet? I think it's something like 3.28 feet. You do not have to have that memorized, but it's about 3 1/3. That's actually what how I always think of it if I have to convert them. 3 1/3 feet is 1 meter. So I am 1.82 meters tall. I am a Homo sapien. So what I'm asking for you to do over here is name of a living structure roughly this size, see link in PPT. You'll see that eventually in the PPT. There's sorry, see link in PPT. So it should be see link in Word document. It's really clear in the Word document. Okay. So centimeters. Centimeters is kind of the world of inches. Centimeter, let's see what, 1 inch is about 2.54 centimeters. 1 inch equals 2.54 cms. Science standard, I'm not going to do this one for you. I'll let you do it. But what we're doing here get rid of that. In this column, all this is our standard notation. Standard notation. And this is maybe I shouldn't have said scientific notation, but it's the exponent version of this, right? So a millimeter, I've already told you that is 1 meter equals 1,000 millimeters. So 0.001 meter. 1 millimeter equals 0.001 meter, or a millimeter is 1,000th of a meter. What we're doing here is I'm asking that you know how each of these units, here's a micrometer, there's a nanometer, how they relate to a meter. So a millimeter is 1,000th of a meter, or 0.001 meter. A micrometer, this is what we use to measure the size of cells, is a millionth of a meter, and 10 to the negative 3. And this one, it's pretty easy, 10 to the negative 6. That's a millionth. That's a billionth. And this is what we use to measure things like big molecules. So you'll have to fill this in the assignment. This, when you follow the link to that is in the Word document, it's going to take you to a website, and that's part 3 here in your assignment. It's going to take you to a website that looks like this, or looks like not like that. Not like that. Doesn't look like that. It's going to look like this whole page here. It looks like all of this. For reference, in case you don't know what a coffee bean is, this would be Times Regular 12-point font, the stuff that you write your emails in. You can grab this fellow over here and you can drag it to the right. And when you do that, you're going to zoom in on more and more smaller and smaller things. This is a grain of rice, that's a sesame seed, and then here you can see there's some other stuff you will eventually see when you magnify these images. I'm going to ask you to write down the size of some of these things, like a coffee bean, and I've asked that you just, so that we all write the same thing, use the smallest measurement, and that's in the directions. I'm just saying it again. So that's the smallest one. Coffee bean from here to there is about 8 millimeters, 8 millimeters. So, and that's a coffee bean. Most of you probably know what coffee beans are. Part 3, the metric system, length and biological structures. So that picture I was just talking about on the last slide, we saw coffee bean, and on the website it tells you that the size, smallest dimension, is 8 millimeters. Then I want you to be able to convert that 8 millimeters to meters, because meters are the standard unit for length, and that would be 0.008, because there are 1,000 millimeters in 1 meter. Next, converting this value to scientific notation. And what that is 8 times 10 to the negative 3. Negative 3 means take our decimal point, that is right after the 8, and move it to the left 3 spaces. Did we do that right here? Let's see. 1, 2, 1, 2, 3. We did. And then I've given you a couple more of the answers here. An E. coli bacterium is about 0.6 micrometers, and what that is essentially a millionth of a meter, 1/1,000,000th of a meter. So you could line up 1,000,000 E. coli bacteria, they live in your gut, and then you'd have a meter, which is about 3 1/3 feet. HIV particle, also similar. The coronavirus is, I can't remember if it's bigger or smaller, but they're both viruses. And now we're talking about nanometers, and it gives you this value on the slide, so you'll be able to see this. And I've done this one for you as well. 130 nanometers equals this many meters. And again, nanometers to meters. I can do this in my head because I know that a nanometer is a billionth of a meter. So 130, let me check my work here. That's where the decimal point, oh wait, no, that's not where it was. It was because it was 130, right? So the decimal point was there. There'd be another 0. I just move it to the left 9 spaces. So starting here, we'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, I did it correctly, and I also got kind of dizzy staring at the screen so intently. And there's the scientific notation. Cool. Ribosomes and phospholipids. I chose a couple of molecules we're going to learn about later. Now you'll know how big they are. Hooray. Zooming in further, this is the E. coli bacterium I was just talking about, and I told you it is 0.6 micrometers in width. So from here to there, that is 0.6 micrometers. And if you're typing in a Word document and you don't know how to find this unit here, don't ask me because I don't either. What I do is I search online and in a Yahoo or Google search, and I say, how do I type a micrometer? And then you'll just find that someone else has written a micrometer, and you can copy paste this thing into your Word document. And so that's where the E. coli is. Hooray! Okay. Part 4, the metric system. This is now back to volume. So we're looking at liters, and remember it's, I think, 1 gallon equals 3.8 liters. Ooh, that's pretty ugly, sorry. 3.8 liters. This is the standard unit, a liter. And what could you measure in the living world? What occupies approximately a liter? I mean, I just kind of guessed here. A house cat. These ones I did for you because you normally don't measure living things in volume. It's usually mass, but just to connect volume to something you might be familiar with, I did this. I filled it out for you. Down here, a nanoliter, that is a billionth of a liter. So if you can imagine like one of those Nalgene water bottles, that's actually a liter. And a billionth of one of those water bottles, that might be what you would measure, like the amount of a drug in that somebody is taking, like an antibiotic or maybe insulin injections, which is a hormone. But this one we're not going to use too much, so I did it for you. That's why. But you need to fill in this blank, that blank, that blank, these blank, all the blanks, okay? All of them. Yeah, okay. The part 5, the metric system. So this refers to part 5 in your assignment. And I'm just going to ask you to do some more calculations. And you're going to need to refer to the table so that you know what things like kilo mean. Kilo, that means 1,000. So that if you have, say, the base unit, which is gram, and I ask you what would be the abbreviation of a kilogram. It is a kg, and you might need to use the internet to get some of these abbreviations, but I'm basically making this a little bit more of a free-for-all, and I'd like you to be able to find some information. The table that I included at the beginning of this PPT has most of the information that you need to know, but you might want to look online if you're finding it a little difficult to find out. Like how would you abbreviate like a kilogram, and you're like, I have no idea, then just look up the abbreviation online. You need to know them. Okay, and here is my final bid to try to convince you that the metric system is pretty useful, at least in science, because it is also related to water in this way. A calorie is the amount of energy required to raise 1 gram of water 1 degree Celsius. So if you are interested in controlling the temperature of something, then you would know that 1 calorie, if you add 1 calorie of heat energy to 1 gram of H2O, then the temperature will go up 1 degree Celsius. So 1, 1, 1. If you added 10 calories to 1 gram of H2O, then you're going to increase the temperature by 10 degrees Celsius, and so forth. And I guess I'll give you one more example. If you added 1 calorie to 1 gram, did I say that right? No, let's say 10 grams. If you added 1 calorie of heat energy to 10 grams of H2O, then you would increase the temperature just by 0.1 degree Celsius. So this first one up here is the one you really got to keep your eyes on. 1 calorie will increase the temperature of 1 gram of water by 1 degree Celsius. But that's not where the convenience of the metric system ends. It gets even better. Let's erase all of this stuff. Okay. Also, 1 gram of H2O equals 1 milliliter of H2O. So mass is related to volume in a really easy way. So 1 gram of water takes up 1 milliliter of space. And what if we use a kilogram? So 1 kilogram of H2O. So one kilogram is, so basically it would be like, if we had 1 gram, so times 1,000, right? Then we'd have a kilogram. In 1 kilogram, there is 1,000 grams. So now I've got a much bigger number here, or a much greater amount of water. 1 kilogram of water equals 1 liter of water. And what do you know? 1 liter of water is 1,000 milliliters. So if you had 1 milliliter and then you went times 1,000, you get 1 liter. And what do you know? 1 kilogram equals 1 liter. It kind of continues in this manner. If we say if we had one metric ton, so that is 1,000 kilograms. If we had 1,000 kilograms, then that is also going to be it's going to be 1,000 liters. 1,000 liters, which also equals 1 cubic. Oh, can I draw this right? Meter. So 1 meter by 1 meter by 1 meter, or 1 meter cubed of H2O. So pretty amazing that they're all very relatable and really easy math. 1 metric ton equals 1,000 liters equals 1 cubic meter. In many parts of the world, they measure your water usage in cubic meters. which in 1 cubic meter is 1,000 liters, and 1,000 liters is 1 metric ton, or 1,000 kilograms. All right, so I think that about does it for the metric system. In lecture, I've talked about the importance of water, and what do you know, the metric system relates mass to volume, even to sort of to length, in this way, just 1 cubic meter is related to volume, and it's all related by, where am I going to write it? I'm going to write it right here. By water, H2O. 1 gram of H2O equals 1 milliliter of H2O equals 1. What would that be? One cubic milliliter, or 1 cubic centimeter? Anyway, there's a cute thing for 1 milliliter equals another 1 cubic something or other in the metric system. Again, I'm not asking you to memorize most of these. I haven't memorized them all myself. So, without further ado, the metric system is pretty useful in science, and you have to know it.